Thank all participants for interested in the third international workshop on advanced topic in dynamical system. This workshop is the third part of our series, which started in 2019. Special thanks to our invited speaker, Dr. Dawoud Ahmadi from University of Guilan, Dr. Nadia Al-Saidi from Technical University, and Dr. Madeleine Tahan from Lebanon International University, and Dr. Radhi Ali from Mustansiriyiah University. Now I would like to invite the Dean of Faculty, Dr. Salam, to start and open the workshop. Please, Dr. Salam.
Yes. Bismillah ar-Rahman ar-Rahim. Assalamu alaikum wa rahmatullahi wa barakatuh. والصلاة والسلام على سيدنا وسيد الخلق أجمعين محمد وعلى آله الطيبين الطاهرين وصحبه الغر المنتجبين. First of all, I would like to thank you, Dr. Ali, for giving us the opportunity to participate in this workshop, the third version of this workshop. And I'd like to express my warm welcoming for all the participants, especially Professor Nadia and Professor Madeleine and Dr. Radhi and all the participants. And I want to express my deeply thankful for the committee of this workshop who did their best to make this workshop done. And I would like to make this workshop. Unfortunately, it is done now virtually, and I looking forward to make this one on our halls. Thank you very much for your participation and giving us the opportunity to participate, and the floor is yours. And I want to express my my thankful for you just in Arabic, just in a few words. بسم الله الرحمن الرحيم. السلام عليكم أخوتي ورحمة الله وبركاته. حقيقة يسعدني ويشرفني أن تقام هذه الندوة بالحلقة أو هذه الحلقة النقاشية بصفتها أو بشكلها الثالث بالمرة الثالثة اللي تقام. الشكر موصول إلى كل أعضاء اللجنة الذين دأبوا على أن يقيموا هذه الورشة بهذه الصيغة، وكنا نتمنى أن تقام حضوريا وليس افتراضيا، لكن نطمح إن شاء الله أن تقام هذه الندوة في العام القادم حضوريا بعد أن يزال هذا الوباء والجائحة. نسأل الله لكم التوفيق جميعا، وشكرا لكم جميعا، والشكر الخاص لبروفيسور نجادي أن كل ضيوفنا، عذرا إن نسيت أحدا، كل الذوات مع حفظ الألقاب والمقامات لإقامة هذه الندوة. شكرا جزيلا لكم، والكلام لك دكتور علي. The floor is yours and thank you very much. Thank you.
Thank you. شكرا جزيلا. طبعا أيضا ممكن يعني almost all of our participants from Arabic area, so I will speak give some words in Arabic. So شكرا جزيلا جميع الحضور لهذه المشاركة، لتفاعلكم والمشاركة في الحلقة الثالثة اللي تمتد على مدى 3 سنوات من 2019 إلى هذا اليوم، وإن شاء الله تكون أيضا كما قال دكتور سلام السنة القادمة في الجامعة. شكرا جزيلا لحضوركم ولمشاركتكم. الآن سوف تبدأ الورشة. إذا كان بعد نهاية أي lecture أو presentation تقدر تفتح المايك وتسأل أي سؤال، أو تفتح الكاميرا وترفع يدك إذا عندك سؤال. فالآن سوف نبدأ الورشة. So let me mention something, please. After the presentation, if you have a question or comments, you can turn on your microphone and ask, or you can turn your camera and raise your hand and ask your question. So now we will start. Dr. Ahmadi, I will send you an invitation. So
Assalamu alaikum.
So now we have the alaikum salam. So now we have the first presentation. Dr. Professor Dawoud Ahmadi Dastjerdi from University of Guilan. The presentation entitled Iterated Function System over Arbitrary Function Shift Space. So Professor Ahmadi, please, your words.
Okay, thank you very much. Thank you very much for inviting me to this workshop. I thank all the organizers, in particular my very good friend, Dr. Shukr. I thank all my colleagues in University of Kufa that provide such an opportunity to gather us together to talk about dynamical system. My very special thank you goes to Dr. Salam, the Dean of Faculty, and Dr. Janabi, and please convey my salam to, yes, Dr. Janabi. So I like to start my talk. This is almost a short talk. I will introduce a branch of dynamical systems that recently, about more than a year, I have been interested, and I think there is a lot of room for that to work together. So, as Dr. Shukr told, the title of my talk is Iterated Function System over an Arbitrary Shift Space. This is a research that I'm doing together with a PhD student of mine, Nadia. So, like everything else, dynamical system has gone through an evolution. Then, in the various stages, I will not take the time, I will not go through the history because there's a lot of histories around that people can go and study by themselves. But I will tell what I'm going to tell about this talk. When I'm saying conventional dynamical system, DS stands for dynamical system, I mean a function like any other dynamical system. Some people call it classical dynamical system, but I have reserved it for the classical iterated function system. So the usual dynamical system I call conventional dynamical system. Then very briefly I will introduce non-autonomous dynamical system and the classical iterated function system. And then what I've written in blue is what I am doing, and I like to find some answers. I have some questions there, and I'm working on it. Okay, so here is conventional dynamical system. Perhaps some people will define it as a group acting on a set X. We will have some properties on X. It can be, here we take it to be a topological space. So what I'm going to say today will be a branch of topological dynamical systems. But my questions go for the case when X is a measure space, so ergodic theory, that we're still working with some colleagues. They have a lot of problems to be solved there. But today I'm just concentrating on topological dynamical system. As I have told above, X is a compact metric space. And I'm considering discrete dynamical systems. Non-autonomous discrete dynamical systems consists of some countable functions, and these are very well known. They start from mid-90s, and still people are working there. This is the path that I'm going, actually, and we will get to where I'm working. Here again, all the functions are continuous, and the case that I am interested, and many people are working there, is the case when the functions here, fn's, are finite. So they are not, the sequence is infinite. Actually, it's a sequence, and any sequence is infinite, but this is infinite sequence, but the functions that I'm considering is the finite sequence. And many people think that this represents more naturally dynamical systems, because if we consider any application of F as an experiment, then during the time, functions will change. So this may be applied to natural sciences more naturally, though many people have not yet used it because there are a lot of difficulties. And this is our job to get better models that can be used in natural sciences, in physics. And iterated function systems. This is we get X, some finite and some finite continuous functions, Fi, again, some finite continuous functions. And what we do as an orbit of a point, in dynamical systems, we are always interested in orbits. Where does a point go, and from where it has come? This is the question we are always facing in dynamical system. So you will get any combination, sorry, I can write on it. Any combination of functions, orbit. So I'm writing in the last line there, you see that. What I'm saying full shift is the usual full shift we read in very elementary dynamical system courses. This is full shift. For those who are not familiar with symbolic dynamics, full shift is here our full shift has cos symbols, and X is that cos symbols, say the set of 1 to cos to the power of z, or n, with n which is natural number, and z are integers. So I think people are familiar with that. If not, then they can ask me. I will, of course, will be happy to answer. So here, here I want to say that how IFS, or iterated function systems, which I was talking in the last page, is related to non-autonomous dynamical systems. I wish I can write on, no, I cannot write. I thought that I can write on this page, I cannot write, so sorry about it. Let me see. No, I cannot write. Okay, perhaps, sorry. So we had when I was defining non-autonomous dynamical systems, it was a combination of functions. We choose X, F2OX, F3OX. And here, what we do is that we choose a point in sigma, and when we look at this one is a very similar to that one, but sigma is a full shift. Let me say here that I can write sigma F is I'm considering as to the power of n here. I'm in this talk, though in our real work we are working on Z, even in other sets. But here, to be as simple as possible, I'm considering on n, and let me again here that I know I can write it. Let me write it that 2 takes sigma 1. This is sigma 2. So just to introduce my notation, sigma 2, it's always sigma 1 and then it starts from sigma 2 as usual dynamical system. Okay. Sorry. Now, and I have, when I am taking a point in my shift space, here perhaps sigma F, I have to write first sigma F. Sorry, this is sigma F. Here on the first one, I have written just sigma. I will turn to sigma later. But then you see that non-autonomous dynamical system arises. So non-autonomous dynamical system inherently is related to an IFS. Here again I introduce the shift map. But what we are doing now, we are going to forget the full shift which is which defines the iterated function systems, classical iterated function systems. We will switch it to a subshift. This is the main job that we do in this research. So we are looking at iterated functions is systems that it is over a subshift. That subshift is full shift. Now we are changing full shift to an arbitrary shift. An arbitrary shift, as I've written here, is uncrossing is a closed invariant subset of the full shift. Equivalently, subshift can be defined by introducing the set of forbidden words. It's very easy to prove that if we say that we don't like to have these words. Words is word or block will be a final sequence of characters. Okay, so then we delete some words, we say we don't like them to have them, or the physical situation will tell us that we cannot have those words, then we will have a subshift. Those forbidden words can be finite, can be infinite, but anyway, because we are working on finite alphabet, in any case, they cannot be more than countable, always they are countable. And as I have written here, when the forbidden words are empty, any word is admissible. If any word is admissible, then our subshift will be full shift. Please notice the F's there. F, Roman F stands for full shift, but Pascal F is for forbidden cells. I will not use it that very much, but just introduce it here. Then we have forbidden word. When we are forbidden word, the other words all are called admissible. Okay. I have to bring some very elementary definitions and facts from the symbolic dynamical systems. One of them is subsheet of finite type. When the set of forbidden sets is finite, you can easily give examples of sets that are infinite. Very easily you can say. Then I need suffix that very famous. The people have worked on them because suffix have some finiteness in that. So any factor, I think I have to say about factor here. Okay. Then we have a SFT. Then we have a SFT. Let me give you a very good example, which is called golden shift. Golden shift is this is very classical one. One is forbidden. Usually we use a graph to represent a suffix because it's a very classical result that any suffix has a finite cover. What we mean by finite cover is this one. For here, we will have here 0, 1, 0. So you travel on this graph. When you are going here, you write down here 0. When you reach here, this is just for people too. When you come to the arrow which has 1, you write 1. When you come to 0, again you write it down. For example, if I come here twice, I will add here 2 zeros, and then I can pass to 0. And so any point of my subshift, which is my subshift now is sigma f, that is the words 1, 1 is forbidden, and you see here that 1, 1 never can happen. If you have 0, then perhaps you may have as much as you want zeros in your sequence representing the point in your subshift. And but when you have 1, after that you cannot have 1. This graph is called a cover for the, actually this system is suffix. This is a SFT, any SFT also is suffix. If I For instance, if I clean up this one and put 1 here, then this will be a suffix. So the suffixes are very much studied because they can be represented as easily as this one by a finite color. Anybody can draw graph like this one and can label the size like this one, 0, 1, or anything that can have, and then can travel through all the passes and generate the system. Okay. So, a factor, I forgot to say factor, anyway, a factor of SFT is Safi. Factor is like any other places in the topological dynamical system. From there is a factor as again writing. Okay. Then we have in topological dynamical system, the factor is defined like this. For example, we have here T, here we have S, X and Y topological spaces, T and S are continuous and phi is continuous. And this is by these continuous because factor. This is more or less the same in symbolic dynamic, except that we do it a little bit different but easier. So, but I'm not going to do symbolic dynamics. I think that I will be, then I cannot do the major things that I want to say, but the main concept is this one, like everybody else. Okay. I need to introduce this synchronize. Two words. Please look at the U. After U comes a V. After U. And VW, the same V comes before W. If they are admissible. Please recall that not all blocks or all words are admissible. When we say we are saying admissible, it means that something is not admissible, something is forbidden. When you have a word like this called synchronizing, that when UV and VW are admissible, UVW is also admissible. Either we can say it is admissible, or we can say it is on the set of words of sigma that have written UVW inside of sigma. Then a subshift which has a synchronizing like V is called the synchronized system. Full shifts that are usually more studied. No, as I told you, F is empty set, it is SFT. So it is suffix because any SFT is suffix. This category grows like this one. All the suffix systems are can be proved that they are countable. All the suffix systems in the dynamical systems are countable. Suffix, all the suffixes are synchronized. Synchronized cannot be represented by a finite graph. Non-suffix synchronized. Not all the synchronized system can be represented by a finite graph. But SFT is a subset of suffix. Suffix is synchronized, and virtually synchronized is the closest category of all subshifts close to to suffix, and as I wrote here, any suffix is synchronized. Why we do need this one? Because we told earlier that the classical iterated function systems are defined, or we can think that they are defined on full shifts, and we have changed it to subshifts. Okay, this is what we have introduced. So it is, we call it again IFS, iterated function systems, and I is a, for X again, compact metric space. We have finite continuous function, but sigma is a subshift. Here, perhaps two functions cannot come together. For example, if I use golden shift, the one that I told you, and one was forbidden, then we cannot have two one together to be combined together. So this is our main object that we work on. Then we define the forward orbit of any x, written down there. It is all when I'm saying fu x, it means I introduce this before. I recommend that I introduce this before. So fu x means combination of the characters in U. Perhaps again in this one I have to introduce it. For example, if U is 0, so U0, U1, say UL. If U is this one, then we write F U of X equal F UL, UL, U1, U, they are all our characters, either 1 up to top, F 0 X. So this is the orbit of the world defined here. Okay. I wrote the definition, very classical properties of properties seen in the dynamical systems. Transitivity is like everywhere in dynamical systems, but please notice that all happens along the rows like U. So admissibility here is the thing that we have always to check. U must be in admissible row. Mixing, again, very common concept in discrete dynamical systems, all dynamical systems. I just go through slowly to have those people who are not familiar just to have a look at it. And exact is highly rich dynamical system, very soon expansive, and very soon of the combination of F5, the zero and open set to be all the E's. Now, these are, I thought, they are very classical concepts. In any IFS, exactness gives mixing, and then this transitivity. Here, and like the non-autonomous dynamical system. When we say a point is periodic, it means that after application of L here until P times of F, we will have S. Again, perhaps I have better to write it down. Why this is not a problem in conventional dynamical system, but here and in non-autonomous dynamical systems, periodic, we have different type of periodic, but I have chosen this one. So the simplicity. And I will tell the point. Look, you have X here. X goes to F. X. This goes to F. Sigma L minus 1 of X, and again to X. But when we are here, it doesn't mean because sigma that here, you see, when we are here, let's study. When we are here, perhaps we do not have the F sub sigma 0, and we may have another one. We have a sigma plus 1. And this one may not be the same as F sigma 0. This is not coming here. This is because sigma L, this one, may be different from this one. So periodicity here happens, it is periodic. In any, you see here, that in any multiple of L, we will have, this will, X will appear, but not between. This is the most natural definition of periodic dynamical systems, non-autonomous dynamical systems, and in iterated function systems. Okay. Now that we have understood, these are our main observations. If we have an IFS and our subshift is suffix, as I told you, suffix is the factor of SFT, and SFT is forbidden set is final, then if we have a periodic point, we will have periodic point. Sigma may not be periodic. Then sigma period, we will have a periodic sigma period. We will have periodic sigma period. That this periodic point along this sigma period is as usual in conventional dynamical system. That is the one that I showed you, that I write it down for you, will not happen, this will happen, that sigma L plus 1 will be against sigma 0. So then this is suffix. Any periodic point guarantees that we find a sigma periodic, that X is periodic along that. Dr. Shukr, please announce the time. How much time I got?
You have more 6 minutes.
Okay, so I will pass through this one. I'm giving here an example that when it is not suffix, the closest subshift to suffix is as I told you, is a synchronized system. Here there is a system, synchronized system, where it is the conclusion of that theorem is not correct. So these are problems involved in our dynamical system. Okay, they are people are no, these are the same as everywhere that it is defined. But I want to notice you that when we are dealing with iterative function system, transitivity has two meanings. Either it is in all the system, the first one, a point is forward transitive, or it is along an orbit. It means transitivity happens like in an autonomous dynamical system. Look, these are very classical results, not easy to prove, but very classical results. Anybody expects that. Either it is forward transitive. For example, the last result is that the set of transitive points are residual in here as well. This is very expecting. Even if it will be our IFS is transitive as sigma, again we have the sense. Okay. Here again, we are saying that if we have an irreducible suffix, sigma is irreducible suffix, and our system is forward transitive, then there is a point in sigma that this point is transitive as well. You remember that I told you when we have periodic, our periodic will have will force us to have a periodic point in our subshift that periodic. The point is where that was periodic at that sigma period. Here again the same happens for transitivity. It is not easy to, we have constructed an example that this is this happens only for suffix and not for other cases. Then we usually ask if we have a transitive point, how many points are in our subshifts? We call this set S. That this can be along that sigma. It is transit. We have not completely solved that, but we have a partial results about that one. Especially I like to know then that this S is residual. We should have some condition on it. Okay. Here I have introduced again the subshift. This is very much like this is like a specification property. I did an specification property down. As usual, are any two boards in our subshift can be. We can travel from a board U along the admissible boards. Would like to have a rule that its length is not greater than m to have another two readable b. So if you put this is called variable gas length, there are very almost non symbolic dynamics. Our result says that if we have the SVGL, then S, the set of the sigma that forward orbit of X was dense, now that S will be dense. Okay. Here we have introduced a specification property. This specification property is not ours. Actually, this definition is not ours. It's written in good literature. You will find this specification property for IFS. It is like a specification property. Perhaps I don't have time. It is very famous. You know that first Bowman specification property, or better to say strong specification property. It means that when you have all that is that this system is very rich. Bowen was interested in finding measures for conventional dynamical systems, and in hyperbolic dynamical system he introduced this one. So when we have a specification property, for those people who are understand that one, this means that a specification property happens along any, this line, second line, along any point in the sigma. Along it. So you have to check all the sigma, all the points in your subshift to see if it is it has a specification property. A very easy conclusion it has. We can find it, or we can prove or find it, that if it is a specification property, it is mixing along any sigma, it is transitive along sigma. So S, the set S, then will be all of the subshift. Also prove that when we have a specification, this is one of almost major results, that you should not check along all the audits, just along transitive. If it is a specification, it has a specification property along just a transitive point in sigma, it has a specification property complete. So here I put some questions. Conventional, I put gray color, they get darker, then we have more questions. And still for non-autonomous dynamical system and classical iterative function system, and again for the one that we are studying, the ergodic problems are a lot of problems that has not been solved. I very much like to see if our conventional dynamical system is the one that Dr. Sugar is expert, linear dynamical system, how non-autonomous dynamical system. Actually, I started to work with it, then I got that I have to strengthen my knowledge of the functional analysis. Again, I hope that we will start working.
Inshallah.
Thank you for...
Thank you. Please.
I'm done.
Okay. Thank you very much for your very nice talk. And actually, symbolic dynamics is a very important part of pure mathematics in applied mathematics. I mean, especially in encryption. So we have 2 minutes. If anyone have a question or comment, so please you can raise your hand. I mean, turn on your camera and raise your hand and ask, or turn on your microphone and ask your question. Of course, I have a lot of questions, but we will discuss it privately. So I think there is no question. So let's thank the speaker again, Dr. Dawoud Ahmadi. Thank you very much, and thank you for sharing your time and accepting our invitation to give this nice talk. Now let me ask Dr. Nadia. Dr. Nadia, if you have, do you have my voice? دكتور نادية موجودة؟ ما أعرف، أعتقد موجودة.
Yes, Dr. نعم موجودة.
دكتور راح أدزكم أو just a minute. نعم أسمعكم. دكتورة نادية، أعتقد الآن جاكم طلب بالبرزنتيشن.
نعم.
دكتورة وصل لكم طلب البرزنتيشن؟ أنا ما جاي أسمع صوتكم يتقطع.
To Dr. Ali for inviting me or for giving me this opportunity. My presentation is about chaos theory and reinforced peer communication. I will go in this presentation through the following outlines, and to those who didn't know about chaos, I will try to give some idea about this branch of mathematics that studies the behavior of dynamical systems. It's actually the words come by Edward Lawrence, the mathematician, and when he studied the weather. It refers to a complex dynamical behavior that persists some special features as being extremely sensitive to some variation in its initial condition. So, for a system to be chaos, it possesses some special features like bounded trajectory, positively open exponent, and sensitivity dependence on initial condition. Here are some pictures from nature that give us or that illustrate the chaotic behavior. Once we for centuries we have no idea about chaos, but once you understand what we mean by chaos, we can see it nowadays everywhere. As I mentioned, that it brings this science bring to us by Lawrence, Edward Lawrence. He is a mathematician and meteorologist, and he is the first contributor to chaos theory and the inventor of the strange attractor. He coined the term of butterfly effect, the most interesting concept in chaos theory. And I will go to illustrate what I mean by butterfly effect. Lawrence studied the weather through a system of three equations, and he takes some parameters. He takes the parameters that is my voice is clear? Please?
Yes, doctor, it's clear.
Yes, is it?
Okay, because I hear some noise. He studied a system of ordinary differential equation, And through this system, he can predict the weather. Here are some examples of the trajectories based on different initial. You can see in this amazing pictures that they behave. Their behavior is chaotic, and the chaoticity depends on the starting point. When they start at any point, it will go to some this trajectory to one of the attractors in any system, as we know, as all of us know, that in any system there are maybe in some systems finite number of attractors. So here each trajectory goes to one attractor, and these pictures show us the behavior of the chaotic behavior depend on the system. And what we mean by attractor, by butterfly effect, the main concept in chaos. There is a known saying about to illustrate the butterfly effect, that if a butterfly flipping its wing in any country, it may cause tornadoes in other countries. That means any small change in the initial condition may cause dramatically change in the behavior of the resulting system. Here in this short video, I will show how computer designed to us or draw the butterfly, how the butterfly is defined, depends on the trajectory. They accumulate on the attractor, depend on the initial condition. If we change the initial condition, we will see another attractor, as we will see now. So it splits the space into here into two regions, depend on the initial condition. We will see some attractor different from another, one of them in green and the other in orange. And here are also show us some pictures, show us the butterfly effect in nature. It also can be shown, obviously, by flock of birds that change their flying patterns depending on their mission. So their behavior is also chaotic, as you can see in this short video. How the species of these birds perform, they give us a wonderful synchronized moving. Another important concept that used to show the chaoticity of any system is the Leibniz exponent. It's a quantity that factors the rate of separation of infinite closed trajectory. Also, it's a quantity used as an indicator of the chaotic behavior. Some of the dynamical system, if they have a positive Lyapunov exponent, then it's considered chaotic. And also in multi-dimension dynamical system, maybe we can find more than one positive Lyapunov exponent, and in this case, this phenomena is called hyper-chaotic. One more important concept related and used as an evaluator for the chaoticity of the system is the bifurcation. This phenomena shows us the distribution of the output with the varying of its control parameter. So it's a quantity change with the changing of the parameters. And I will show in this short video how by changing the parameter A, we see that how the bifurcation is formed. It's like begin by give us how the point is split, how to start the bifurcation. So it depends on the changing in the parameter and how it's meet the plane. The trajectory here is give us, depending on the change in the parameter A, the bifurcation behavior of the system. There's two types of chaotic. Chaotic is constructed from two types of systems, continuous or discrete. Example on continuous system, Lorentz system, Kreuzer system, and example of discrete system is the logistic map, sign map, and Keenan map. Here are some examples of this system and the year of their invention. When chaos meets other disciplines, we see nowadays it's used in many other disciplines like physics, engineering, medicine, biology, finance, art, economy, and many other disciplines. I will focus in this presentation on using chaos in communication, and I will illustrate later why we use chaos in communication. If I want to go through some mathematical properties of chaotic systems, it should be dense, it should be transitive, and it should possess sensitive dependence on initial conditions, as I mentioned before. These definitions are, you can find it everywhere. So for any system, for any map, it's called chaotic if it's processed through these three mathematical concepts, that if is transitive, the set of periodic points is dense, and if is sensitive dependence on initial condition. The efficiency, if I want to prove the efficiency of a chaotic map, I have two ways, the mathematical analysis and the geometric technique. The first one through fixed point, Jacobian eigenvalues, and the second one through the trajectory, the Lyapunov exponent, the bifurcation, and the approximate entropy. I will focus here on one paper published lately, and Dr. Ali asked me regarding to this paper to present this subject. In this paper, we and my students propose a new hyperchaotic system. This system is derived from one-dimensional sign map. We modified it to two-dimensional sign map, and this new system, the efficiency of this new system is approved, and I will show you how this system shows high chaosity in its behavior, and we use it in one of the application in communication to encrypt message sending through an optical channel. This system has many fixed points, and here I take some example of such fixed points and show the stability analysis of these samples. Also, the trajectory of this system shows that it has a high chaosity because we observe that the separation, the system is separate on a wide range on XY plane, which indicates that it has a good distribution, and it has the property of unpredictability. It's too difficult to predict the points, the behavior of points in this system. Also, through the Lyapunov exponent, we demonstrate that it has more than one positive Lyapunov exponent, and this is also an indication for the system is chaotic, and moreover it's hyperchaotic because we have more than one positive Lyapunov exponent. It depends on the range of the parameters of the system. Also, another property is the bifurcation diagram. We see in this image that the bifurcation, the solid line refers to a range when the system is periodic, and the dotted line are an indication for the region of chaotic behavior, and we see that it has a wide region of chaotic behavior. Also, the other evaluator factor is the approximate entropy. It's based on the parameter alpha in the proposed system, and we can observe that the system is chaotic because it has high complexity measure from the value of the approximate entropy. After we evaluate the proposed system using the geometric parameters with the Lyapunov, the bifurcation, the trajectory, the approximate entropy, we will use it, or we used it already in designing of an encryption system to secure a communication channel. The motivation for using chaos in communication, as all of you know, that modern communication technology, especially internet, mobile phone application, need to transmit many kinds of digital data over the wireless network. So these data need to be secured. How to secure it? The researcher working, and there is a growing demand for new cryptographic techniques to protect the transmission of this data through unauthorized channels. So chaos in 1990 showed that there is a strong relationship between chaos and cryptography due to its properties, which is unpredictability, randomness, sensitive to initial value and parameter. However, they use in communication, strongly used in communication, and we can find thousands of previous works in this regard. Here are the designed communication system that use an optical channel to transfer data. So the data before transferring is modulated using delta modulation and then encrypted. After sending through optical channel, there is we use the same delta modulation to decrypt the system, the proposed system. Here are the design of the delta modulation that used in the transmitter and in the receiver part. And here is the full semiconductor laser communication system that show us the design of the two-stage encryption and decryption and the sending information through the optical channel. Here are the Arduino board. My student has designed this board and use it. The previous one is the transmitter, and here is the receiver circuit. Some simulation results using MATLAB show us the behavior of the chaotic system, and these results using what we mean, what I have to say, this is called oscilloscope, sorry. So using oscilloscope, in laboratory, he demonstrates that the practical result is have a small error with the practical result, very small error, and he demonstrates this result through practical test. And these are the results of the oscilloscope that look like the previous result of the simulation using MATLAB for the system. And here the encryption and decryption results using the design circuit and using the oscilloscope. The security of the system is proved through entropy measure that measure the random behavior of the data. We get an perfect entropy value, and also we use the NIST test, the 16 randomness test, to show that the proposed system will pass all of these tests, so it can be considered as a secure system. And here are some conclusions of our proposed system that show that the proposed system is hyperchaotic, and the performance of the system is proved through exponent bifurcation diagram and trajectory. In the paper, we compare the system to other known efficient system, and we found that our proposed system gives a better result than the other. We conclude that our system is appropriate for data encryption sent through optical channel, and simulation result is match the practical result using electronic circuit. This is the published paper, the lately published paper about this work.
صحيح يجي يشوفه ولا ترى هاي الاكس غيرناها وكيشناها وين
The stability analysis of the system, the proposed system, and the dynamical behavior, comparing to other here it compared to other existing systems that already published, and we show that how our proposed system gives a better result than the other. Here are the complexity through sample entropy. Here are the diagram for the proposed secure communication system, the transmitter circuit, and the delta modulation, the encryption process, and the program, and the result of the oscilloscope. This is the design circuit. And here are the simulation results. Thank you for your attention. I'm ready to answer any questions you have.
Thank you very much. Thank you very much, Dr. Nadia, for your wonderful talk. And actually, this is to myself that in origin I was I studied a pure mathematics. And recently in 3 years I moved to applied mathematics, so I could understand something. I want to share it, that pure mathematician is like a philosopher sitting in a cave, and applied mathematician like nature scientific adventure. So the difference is very huge.
Yes, it's exactly a bunch of stuff.
Yes. So, okay, if someone have a question or comment, so please you can turn on your microphone and ask. أيوة، أي شخص عنده سؤال ممكن أن يفتح الميكروفون ويسأل، أو يفتح الكاميرا ويرفع إيده للسؤال. و تقريبا احنا عندنا وقت دكتورة نادية تقريبا بعد 7 دقائق إذا أحد يحب يسأل.
Can I ask a question?
Yes, please.
Thank you, Dr. Nadia, for your nice talk. Actually, I wanted to know if there is a relation between the growth rate of fixed points and Lyapunov exponent. So as you said, Lyapunov exponent is a feature of having a chaotic system, but having fixed points is against being chaotic. So in your work, I saw that you are verifying the fixed points. So I wanted to know if there's a relationship between the growth rate of periodic points and the Lyapunov exponent. I mean, can you say, for example, if the Lyapunov exponent is non-zero, then, for example, the growth rate of periodic points is limited? Thank you.
Thank you for your question. As I mentioned, that through fixed point we see the behavior. We have to find the fixed point to study the behavior of this fixed point. Some of them may be stable, some of them may be asymptotically stable, and some of them are unstable. We will looking for the unstable fixed point to recognize the behavior of the chaotic. For the Lyapunov exponent, the value of the Lyapunov exponent, as you know, it can be found through some, through some functions or system have to be solved to find the Lyapunov exponent. We will get some of these values are negative, some are positive, some are maybe zero. We recognize
has some relationship with the entropy. So I wanted to know that if in your system when the Lyapunov exponent is positive, can you say that the growth rate of the periodic points is controlled by, for example, the entropy?
You mean by solving the system, we can find the fixed point. When we solve
the growth rate of numbers. I mean the number of periodic points of period n in some systems is, for example, less than e to the power of entropy.
Yes.
I wanted to see if you have seen this feature in your work or not.
In our system, you mean in the proposed system?
Yeah.
In the proposed system, actually, we found the Lyapunov exponent by programs using software to find the Lyapunov exponent. And also this system have an infinite number of fixed points, so we take some of them to study their behavior. We found that the large number of the fixed points are unstable, but also there is a periodic point, there is an stable point. So in our system we look for the unstable system. So we found that most of the fixed points are unstable, and this is an indication, this is a theoretical indication for the chaosity.
Thank you, Dr. Nadia.
Thank you for your question.
Any more questions?
Dr. Radhi, can I give a comment, please?
Please.
Yes, please.
Thank you for your thought. But I want to bring to your attention, showing some pictures is not dynamical system. When you say dynamical system, some dynamics must be there. That is fractal geometry. I can show you many fractal objects that do not have any interest in dynamical system. When we say dynamical system, must have a dynamic. Some points must move to some other points. Yes, some places you show, but showing, I see people show pictures and even it is not chaos theory. For me, when you show chaos, you have three types of chaos. And most of all, when you are not talking about chaos, we are talking about even chaos. As you told me, it is sensitive to initial conditions and or the periodic point odds. Yes, this is very first this one. Second, I'm not. I didn't understand how you applied it to communication theory. Because if in communication theory, when entropy has the different definition, different properties or different concepts, it gives you different concepts of the system. When you are looking at Shannon uses it for communication. When entropy is high, that means that you are in good position because entropy is then the average of long-term information getting from system. So if you are designing a system, I'm saying the way that Shannon is doing, and the entropy is high, then you have a good system. Actually, you are sending information to the channels more than when the entropy is higher, you can send information more than the case when it is low. So we have to be careful. Sometimes we do not have any fractal geometry. For example, consider Z going to Z squared or Z power of t. This is very chaotic system. But the points that is representing a circle, and circle does not have any fractal geometry. Circle is a very nice math. Very nice math. But in that manner, we have dynamical system. Very high entropy, but no fractal geometry. So we have to differentiate, we have to distinguish between fractal geometry, entropy cases, and dynamical system. I believe that dynamical system actually was the equation that we were giving was working on communication system. And you were showing that how it's working. I understood some of that, but I'm telling that we have different interpretation for entropy in different situations.
Thank you, Doctor. Thank you for this note. Actually, if you put on the future this sequence hand them a very high run that how to prove the randomness is generated sequence. So the characteristic random sequence to be used any cryptography the important sequence cannot be predictable due to the properties of the chaos that match the
This session is no longer being recorded. The recording has started.
do you have me? Or do you have me, please?
Yes, we have your voice.
Okay.
Yes, because the confusion on diffusion of you mean the main properties of Shannon entropy are satisfied with this generated sequence through the high-performance chaotic system. So for this reason, they use it in cryptography purpose. But if you talk about fractal vector, to your interesting lecture, I see that you focus on iterated function system. My main specialist field is fractal geometry. As you know, that iterated function system is one of the methods for generating fractals. Based on their function that should be constructive and affine transformation. For fractal, it is so deterministic and cannot be used for any cryptography. But for chaos, due to its properties, it can be involved, strongly involved in cryptography. I don't know if I can
Dr. Nadia.
answer your question.
Thank you very much, Dr. Nadia. And actually, we are on time. So, thank you very much, Dr. Nadia, for your talk and presentation. Also, thank you for questions and comments. Now, so let's thank the speaker. And now we have our third speaker, and let me share the presentation. Dr. Madeleine Tahan from Lebanon's International University. I need to find you here in my contacts to send invitation, but I think you are okay. I am looking to find yes, so now I will send an invitation. So actually algebraic dynamics is a very modern area in applied mathematics and actually also in pure mathematics. And today we have a special talk outside of dynamical system, but related in somehow to dynamical system, because algebraic dynamics is a very new area, and Dr. Madeleine will talk about also a very special and modern area in algebra. So we have now Dr. Madeleine Tahan from Lebanon's International University will talk about neural-ordered algebra theory and examples. Please, Doctor.
Are you seeing my screen?
Yes. For me, I am, but I don't know if others also.
Hello, everyone.
So if somebody have a problem, please share it with us.
Okay, hello everyone. I hope all of you are safe and in good health. I'm Madeleine Tahan from Lebanese International University, Lebanon. It's my pleasure to be with you today to present a talk about neutral algebra. First, I'd like to thank the organizing committee for IWATD Act 2021 for inviting me to be a part of this international workshop. A special thank you goes to Professor Ali Shukr for his follow-up in the organizing committee. This talk is entitled Neutral Ordered Algebra Theory and Examples. First, we're going to review some basic concepts related to neutrosity. Also, we're going to discuss neutral algebra. Next, we're going to be presenting some of our results related to our new defined concept, neutral ordered algebra, and compare it to the well-known concept, ordered algebra. Finally, we're going to leave some questions that open new research options in this field. So let's start a little bit with a history about neutrosity. Neutrosity is a new branch of philosophy that studies the origin, nature, and scope of neutralities, as well as the interaction with other spectra. The old dialectics, they deal only with dynamic opposites, whereas neutrosity, it deals as well as their neutrals altogether. Actually, this mode of thinking proposes new philosophical principles and laws. It interprets the uninterpretable. It regards from many different angles all concepts, systems, showing that an idea that may be true from a certain referential system, it may be false from another one, and of course vice versa. Also, it measures the stability of unstable systems and instability of stable systems. So if we denote by A an idea or a theory or a concept, non-A, it means that it's not A. And by anti-A, it means that it's the opposite of A. And when we say neutral A, it means it's neither A nor anti. To understand this concept, let's present some examples. So if we deal with colors, the white color as an idea A, then anti-A is the opposite of white. And the opposite of the white color, as you know, is the black color. Now by non-A, we mean any color that is not white, which may be green, red, blue, yellow, even black. It's not white, so it's related to non-A. But when we say neutral A, it means that it's any color that is not white and not black. And when we say A prime, it means that it's any shade of white, like dark white, off-white, or anything else. Another example, if we deal with love as an idea, so anti-A or anti-love, it will going to be the hatred, which is the opposite of A. But non-A, it will going to be any feeling except love. And of course, neutral A, it will going to be any feeling except love and hatred. Here we have some important properties relating the neutral A with the neutral of anti-A. Both of them are equal to each other. The anti-A, as we saw before, in this example, the anti-A or the neutral A theory, it's inside, it's a subset of non-A. So every idea A, it tends to be neutralized, diminished, or balanced by non-A ideas at a state of equilibrium. And between A and anti-A, we have infinitely many neutral ideas. So to neuter an idea, we need to discover all its three sides. These tense one, which denotes the truth, or capital T, the non-tense one, which denotes the falsity, or capital F, and the undecidability, or indeterminates the capital. Now what's the motivation beyond introducing neutrosity? As we know, in sciences, the laws are interpreted and reinterpreted. In political legislation, the laws are flexible. The same law may be true from the point of view and false from another one. Thus, the law is partially true and partially false, and this is what we say neutroscopic law. As an example, if we are dealing with wearing clothes from animals' leather or fur, there are people supporting it because fans feel cold during the winter, and they are right. And people supporting that right because killing animals to get leather or fur. Right. So here we have two propositions. Both of them are true, but from different logic. How can we solve this? As we trust that wearing leather are bad or not from animals, it means that synthetic leather or fur. Another example, if we talk about drug legislation, many people in my country, Lebanon, this for economic because they want to save their face from drug and oil. So here again, we have two opposite propositions are true, but different criteria and different again, the Lebanese law uses medicine and prohibits traders from selling drugs to individuals by monitoring the process, starting from planting to distributing and manufacturing. Okay, now here we are done talking about the mutuosophic ideas. Now we're going to discuss the motivation beyond introducing the mutual algebraic systems. As we know, in classical algebraic compositions on a given set are well defined. But this is a restrictive case because there are many situations in sciences when a law of composition defined in a set may be only partially defined, which is known as partially true, or partially undefined, which is known as partially false, and that we call defined or totally and again in all classical chapters like associativity, commutativity, find a certain set to again there are numeric equations in the domain of between partially true and partially false, and that we call neutral axioms, or it's totally false and that we call anti-axioms. Based on this, Florence Smarndish in 2019 obtained new fields of research, and he called them neutral structures and anti-structures respectively. Now let's define exactly what we mean by neutral operation. Then we're going to define what we mean by neutral axiom in order to introduce neutral algebra. So for neutral operation, we are starting with a non-empty set, as we do usually in any algebraic system. We have an operation on A. For this operation, to name it as neutral operation, these conditions should be holding. It means that we should be finding a curve xy in A square such that x dot y is in A, and this condition for sure we're going to name it as degree of truth, and we're going to denote it as S. Also, we should be finding a curve element such that the product or x dot y is not in A, and this condition we're going to name as degree of test. Also, we may be finding x and y in A such that x dot y is indeterminate, and this condition we call it as indeterminate. Now these three conditions, we have here T, we have I, and we have F. TIF, it should not be equal to 1, 0, 0, y, because if TIF is equal to 1, 0, 0, it means that all the variables satisfy condition 1. It means that x dot y belongs to A whenever x and y is in A, and we are returning back to the definition of the normal or the usual operation. Also, TIF, it should not be equal to 001, because if it's equal to 001, it means that for all x, y in A, x dot y is not in A, and here we have anti-operation. So it's outer default. Here we have some illustrative examples to illustrate what we mean exactly by neutralization. So if we go back to the set of real numbers, we define the division on it, we can say that it's a neutral operation. Why? Because if you look here, x over y, if y equal y is not equal to 0, we're going to get a real number, so it's inside the set again. But if y equals 0, x over 0 is on the point, so here we have t and I, it means that it's a neutral operation. Now, if we change this set, and we are dealing now with the set of natural numbers starting from 1, and we are using the same operation. If you look here, x over y, it belongs to n, if y divides x. And it's not an n, it's not a natural number if y does not divide x. So here we have a neutral operation. Some elements, their operation or their division is inside the set, and other elements, their division is not inside the set. If we look now at example 3, we are changing again the set and using the same operation. We are using now the set of integers. So if you look here, x over y is in z if y divides x and y is not equal to 0. It's not in z if y does not divide x and y is not equal to 0. And it's undefined if y equal to 0. Now we still need to define something known as neutral axiom, and then we're going to be ready to define neutral axiom. So here we're going to start with the universe of this course as the set U. We have also some well-defined laws, and we have as a subset of U, and we have a certain axiom alpha. By an axiom, we mean like commutativity, associativity, we mean, let's say, distributivity, so it's any axiom. If we have some elements in alpha that verify the axiom alpha, if all elements of X they verify the axiom alpha, we have the classical axiom, or we name it simply as an axiom. Now, if some elements verify the axiom alpha and others do not verify the axiom alpha, we name it as a neutral axiom. And if no elements verify the axiom alpha, then we name it as anti-axiom. So here we have a neutral suffix triplet axiom. We have axiom, we have neutral axiom, and we have anti-axiom. If you look here, neutral axiom union anti-axiom is equal to the non-axiom, and the intersection between neutral axiom and anti-axiom is empty. As an illustration, we're going to take our axiom to be the associative. We're going to define now neutral associative. We have a certain set A, this certain set to be with a certain operation or neutral operation to be a neutral associative. We should be able to find these elements x, y, z till g such that x, y, z it satisfies the associativity and we name it as true. ABC it does not satisfy the associativity criteria and we name it as degree of falsity or half. And EFG satisfies the indeterminacy. What we mean exactly by it, either A dot F dot G is indeterminate, or E dot F then dot G is indeterminate, or we are not able to determine whether these two ones are equal or not. And again, of course, TIF shouldn't be equal when 0, 0, and it should not be equal 0, 0, 1, because we do not meet the axiom nor the anti-associative axiom. After defining the neutral operation, neutral axioms, we are ready now to define neutral adjectives. So if we have a certain set, of course it's not empty, and it's endowed with some n operations per I, we can name it as neutral algebra if it has at least one neutral operation and one neutral axiom, in a way that it does not have any anti-operations and any anti-axiom. Actually, neutral algebra is a generalization of partial algebra. And the comparison between partial algebra and neutral algebra. In neutral algebra that has no neutral axiom and no author-defined operation, it coincides with the partial algebra. And we can find neutral algebras that have non-neutral operations, but they have neutral axioms, and then they are neutral algebras, but they are not partial algebras. Also, there are neutral algebras that have both neutral operations and neutral axioms. Let's present some examples because already we illustrate the neutral algebra or the neutral axiom by neutral associativity. So here we're going to give some examples on neutral semigroup. In neutral semigroup, it means that we have a set with an operation or neutral operation that has the neutral associative law. So here again, if we take the set as the set of positive real numbers and we take again the division, we can say that it's a neutral semigroup because here first the division is well defined and we have also the neutral associative axiom. Because if you look here, the neutral associative axiom or the associative axiom, it's this satisfied when z equal 1 and it's not satisfied otherwise. Also, if you look at this table, if we take the set as on two elements, A and B, if you look at this operation between them, B dot B is undefined. So here we have a neutral operation. Also, we do not have anti-associative. So we can name it as a neutral semigroup. Here also we have another example, also in a set of two elements. When we have a neutral operation, it means that some elements are inside, some elements are not inside. Also this one we can name it as neutral semigroup. And finally we have this example, when B dot B is undefined, we cannot decide whether it's A or whether it's B, so it's indeterminate. Also this one, it's an example on neutral semigroup. Okay, now we need to introduce neutral ordered algebraic structures. But before introducing neutral ordered algebraic structures, we need to recall what we mean exactly by an ordered algebraic structure. An ordered algebraic structures, it consists of an algebra A with some partial ordering on the underlying set. We require that the operations of the algebra are compatible with the partial ordering, and this what we name it as monotone property. Actually, ordered algebraic structures carry a wide variety of areas such as partially ordered vector spaces, lattice ordered groups, relation algebras, and many more. As a formal definition of an ordered algebra, if A is an algebra with an operation and we have a partial order on it, by a partial order we mean reflexive, antisymmetric, and transitive, then we can consider A with these operations and this partial order as an ordered algebra if it satisfies the monotone property, and this is the monotone property that we are talking about. So, if you have an algebra with partial order on this algebra, then we can solve the monotone property, we're going to get something known as ordered algebra. Inspired by the neutral algebra and the well-known ordered algebra, we introduced recently in 2021 neutral ordered algebra. Starting with a partial order on a neutral algebra, we get a neutral structure. The latter, if it satisfies the condition of neutral order that we're going to be defining it in the next slide, it becomes a neutral ordered algebra. So here we have a formal definition of a neutral ordered algebra. So again, we're going to start with a neutral algebra. It has n neutral operations or operations. We have also a partial order on this set. Then we can consider the whole set as a neutral ordered algebra if these conditions are satisfied. We need the degree of truth, we need the degree of falsity, and we need the degree of indeterminacy. The degree of truth, it means that we should be able to find x and y in A, x is not equal to y, and such that z star I x less than or equal z star I y, and x star I z less than or equal y star I z for all z in A. Okay, what about the degree of falsity? It means that we should be able to find x and y in A such that, and also we should be finding z in A that does not satisfy the monotone property. It means that it doesn't satisfy either z star x less than or equal z star y, or x star z less than or equal y star z. The indeterminacy also, it can be defined in the same way, and of course, as usual, TIF should not be equal 1, 0, 0, and it should not be equal to 0, 0, 1. Of course, if the partial order that we're dealing with is total order, then we name the whole structure as a neutral total ordered algebra. And we're gonna introduce now the sub-algebra, subset of this one. For a subset of a neutral ordered algebra, to name it as a neutral ordered sub-algebra, it should be a neutral ordered algebra. It means that it should be satisfying these conditions, and extra condition, this one, the brackets x, all elements that are less than or equal to x, they should be subsets x for at least one element x in x. And of course, a neutral ordered algebra, it has at least one neutral ordered sub-algebra, which is x. So, as a special case of neutral ordered algebra, we have something known as a neutral ordered sum. So, for neutral ordered algebra, we are starting with a neutral algebra with a partial order. For neutral ordered semi-group, logically, we're going to be starting with neutral semi-group and a partial order on it. Satisfying these conditions, and of course, TIF, it should not be equal to 1, 0, 0, and it should not be equal to 0, 0, 1. In order to understand what we mean exactly by neutral ordered semi-group, we're going to present some examples. So here we have a finite set S1, 3 elements it contains SAM. This is the Taylor's table of A. Actually, this one is the neutral semi-group under this operation because it's associative for some values and not associative for some values. It's associative for the value or for the element, the triplet as and it's not associative for the triplet as AM. So this is a neutral sum. Now we need to define an order on it. Let's define this order. This order actually it's a total order. We define it in this way. This one, with this partial order, it's a neutral ordered semi-group. Why? Because if we take M, it's less than or equal to S according to the partial order that we define, and we have this neutral order is satisfied. And also we have S is less than or equal to A, but this order or this monotone property does not hold. So the monotone property holds for some elements and it does not hold for other elements. So we have here a neutral order. So this one we name it as a neutral order sum. Here also we have another example on a set of 4 elements. Here we are presenting some examples on finite set. We're going to be presenting also on an infinite set. Here also we have another one on a set of 4 elements. So what about giving an example now on an infinite neutral ordered set? If we take Z as a set of integers, we define the operation O dot as x O dot y equal xy minus 1. This one is a neutral sum. Why? Because the triplet 0 and 0, it satisfies the associative act. Whereas triplet 0 and 2, it does not satisfy the associative axiom. So this one, it's a neutral sum. Now, to be neutral ordered semi-group, we need to define partial order in it. We're going to define the partial order in this way. Minus 1, we're going to put it in the middle. It's our minimum element. Minus 1 is less than all the values. And we have A B or negative, for A to be less than B, then A is in reality greater than or equal to. What we mean exactly by this one, it means that minus 1 is less than minus 2, less than minus 3, and so on. And also, minus 1 is less than 0, less than 1, and so on. This partial order, it defines a neutral order on Z, and if you look here, some elements, they satisfy the monotone property, and other elements do not satisfy the monotone property, so we can say that it's a neutral ordered semi. Now regarding neutral ordered semi-groups, always in any algebraic structures, we are interested in the subsets of this algebraic structure. Also, when we define neutral algebraic structures, we're going to be also, let's say, interested in some subsets of them. So, by considering a neutral ordered semi-group a subset of it, we can say that it's a neutral ordered sub-semi-group. It means that it should be a neutral ordered semi-group satisfying this condition. To be a neutral ordered left idle, it should be a neutral ordered sub-semi-group, and we should be having also an extra condition. The extra condition, we should be finding X in M such that R dot X is in M for all R, and neutral ordered right idles are defined in the same way, and neutral ordered idles are defined in the same way. At least if you have any problem, let's say in viewing the screen or hearing me, or you have any question, you may stop me anytime and ask about it. I'm just gonna check my phone to check how much time do I have.
You have about 5 minutes.
5 minutes, okay. So we define the neutral ordered semi-groups and the subsets of it. Here we have examples on a certain subset of it. We know that in algebraic structures, the non-empty intersection of ordered sub-semi-groups is again an ordered sub-semi-group, but here it's not necessary, and here we have an example. We have two neutral ordered sub-semi-groups. Their intersection is not a neutral ordered sub-semi. So it means here that the known results on ordered algebraic structures, they do not hold from neutral ordered algebraic structures. Here we have another example on neutral ordered idle. If we go again to the neutral ordered semi-group that we defined, taking I in this way, it's a neutral ordered idle because it satisfies the conditions of neutral ordered idle. Okay, I guess because I have 5 minutes, I still have something to talk about, which is production on neutral ordered semi-groups. I prefer to end up with a conclusion right now, and hopefully in another talk we can discuss it. So again, mostly in abstract or perfect spaces, we have rules and rigid axioms that they are totally true. But these ones, in life, we should be more flexible. Because of that, in neutral algebras, the introducing of it is very important. Such a class of neutral algebras is very large. In this talk, we just presented a special type of neutral ordered algebras, which is neutral ordered semi-groups. Many other different types of neutral ordered algebra can be defined. We can leave some related open questions. Can we find the necessary and sufficient conditions for the product of neutral ordered semi-groups to be a neutral ordered semi-group? Also, we know that the steady number in algebraic structures, usually researchers dealt with algebraic structures with finite orders by finding all algebraic structures of this finite order. So here, if we are given a finite set, can we classify all the distinct neutral ordered semi-groups on A up to neutral strong isomorphism? Also, can we apply the concept of neutral ordered algebra to other structures? Semi-groups like, let's say, semirings, groups, modules, let's say, and other algebraic structures? The results in these presentations are from joint work with my collaborative team, presented by Florence Marindesh from New Mexico University, USA, with Bishan Dawoud from Yazd University, Iran, and with Osman Anis from Lebanese International University, Lebanon. Here we have some helpful references if you are interested in knowing more about this topic. And finally, thank you for your attention. And please, if you have any questions, let me know, or you may send it via email.
Thank you very much, Dr. Madeleine, for your very nice talk. And actually, as I mentioned, that algebraic dynamics is a very modern area in dynamical system, and today we had a very special talk from outside dynamical system. But I'm sure Dr. Ahmadi, if he is still here, he have some question, some comments, let's say. And please, if anyone have a question or comments.
Dr. Shukur, why me?
Because I know you.
Thank you very much. It was a very nice talk. It's a new horizon. And actually, I believe if they combine this, somehow this probability theory, they need to combine it with probability theory to achieve some information and some achievements as we did in channel theory of information. When we are quantifying, some aspects that yesterday we didn't know that it can be quantified. It is interesting. I will look at the talk again. I will look at the talk, and I'm actually very happy that in our countries people are working on the edge of science. For sure, this can be applied. Dynamical system can be applied here. But first, I'm not sure. But I think if they apply some probability theory, then algorithm theory is a very good tool for working in this area. Dr. Madeleine, have you seen ever anybody using probability theory in this field?
Please, may you repeat your question because I'm not able to hear you properly. Have I seen whom?
Have you ever seen anybody use probability theory in this field, in this discipline?
Probability theory, you mean? Yes, there is something. Actually, in neutroscopy, when it was defined as logic. Then it was defined as neutroscopic sets, as a generalization of the quasi sets and intuitionistic quasi sets. Also, they defined neutroscopic probability, but it's not related to my domain. Actually, my domain is more related to pure mathematics, which is about hyperstructure theory. And I work a little bit with neutroscopy from algebraic point of view. But there are many applications for it. I can write for you the name of the founder for this new topic. He's Florence Marindesh. On his site or on his personal page, he has all the data about everything related to neutroscopy.
Okay. And how would you relate it to the origin of the life? When we started, you thought that you are going to talk about a discipline which actually is related to the origin of truth, origin of something I forgot.
Okay, you mean how did I think about it to relate it to algebraic systems? And now usually in mathematics, in pure mathematics, algebraic systems, they satisfy rules. And all the elements inside this algebraic system, they should be satisfying the rules. In real life, these rules, they may be violated. It means that a certain rule, and let's say in Iran, it's a rule, and abiding to it is very important, whereas let's say in Lebanon, it's not important, and vice versa. So a rule or a certain idea may be true in from a certain reference point and false from another one. So because of that, the neutral structures are important. And also when we deal with applications in real life, they may be satisfying some algebraic structures, but not all elements in it they satisfy the rule. So because of that, we can name this one as a neutral, because some elements they satisfy, other elements do not satisfy.
Thank you very much. When we have algebra, when we have a structure, we will have a lot of things. We can do a lot of things with it. I mean, it's very nice. I enjoyed it.
Thank you very much, Dr. Ahmed, for your comments. Any other comments or questions? So if there is not, so let's thank the speaker again. Thank you, Dr. Madeleine, for your nice talk. And let's now see Dr. Radhi. Yes, Dr. Radhi. الآن دكتور أرسل حضرتك present invitation. دكتور تسمعني؟ دكتور أرسلت حضرتك invitation للpresentation. دكتور إذا أمكن تخليه full screen. So now our last talk will be presented by Professor Radhi Ali from Al-Mustansiriyiah University. We'll talk about an optimal control problem, formulation, and examples. So, please, Doctor.
Thank you very much, Dr. Ali. First of all, I would like to express my deep thanks to all of you, especially Dr. Ahmadi. He will say why I am, because his comment will motivate all of you all. So I would like to talk about an optimal control problem formulation and example, which is related in mathematics and pure mathematics has a wide range of application, and this area it has to looking for the optimal system design, and the aim of this problem is looking to determine the input that set a system for given for any dynamical system or the system in discrete or continuous, and we're trying to optimize the behavior of such a dynamical system. So I'm trying to discuss with all of you some problem of such an area and how it is optimal control problem can be defined first of all. First of all, what is the objective of the optimal control problem? It is looking for a signal of control, but enable a process simultaneously to satisfy some physical constraints based and maximize or minimize some objective function which has to be defined according to the decision maker and the nature of the problem. So where is the optimal control coming from? First of all, optimal control information one has the main basic definitions has to be, first of all, a mathematical model to be controlled, and the description of the physical constraint and specification of cost functions. Definitely, a mathematical model is the main task. So, let us talk about any control system or any dynamical system to be controlled. We call it a process, because we have to make this is simultaneously based on the nature of the input. Now, let us first of all, what do you mean by plant? Plant is any control process to be controlled, and where is this mathematical model is coming from? So, as you know, mathematical model may be derived mathematically or empirically or symmetrically, and based on the how many data nodes bases do we have. So, if you are looking for the mechanical system, maybe a differential equation is coming from this definition. Differential equation means even ordinary differential equation, partial differential equation, integral, etc. Also, there is a transfer function. Model is coming from the physical nature, and the most important passage is state space model, which are looking for the smallest number of these variables that can be used to describe the nature of any dynamical system. Definitely, for finite dimensional systems, this state space model represents a coordinate of the systems, state space and dimensional coordinate space, etc. So once a mathematical model is developed or derived, then we have to look for how many input do we have on such a system, and how can we design such an input in based up to our knowledge. So let us, first of all, I have to talk about a very simple mechanical system, composite mechanical system. How can we derive a mathematical model from such a system, just to make everything clear? I know it is clear for everybody here, but let us talk about, we have a very simple mechanical. There applies also external force, so we have all forces here, and all of these are affected to the dynamic system, represented by as a displacement from the rest of the system. And if we know from the Newton's law of motion, we have a force. From Hooke's law, we get this cross force. All of these forces together have affected our dynamical system. Now, how can we derive? We have one force, two forces, three forces. These forces are retarded forces. These forces definitely trying to observing this system is clear in the car in our body, which is called dash push system, or it's called observation of system, trying to absorb all the disturbance affected by the weight of such a system. Definitely, we have the mass forces, vector force, supreme forces, external forces. And as you know, all of these forces depend on the output, which is named the y-direction displacement. So if you put all of these together, we have got an ordinary differential equation of a second order with a chord, like chord here. As you know, so one has to solve all of these ordinary to get the displacement and to looking for the effect of the chord concept of displacement. Definitely, from such an ordinary differential equation, we are looking first of all, how can we design a state space model? State space model, we have to looking for the best up to our knowledge and dimensional independent coordinate that can be used to describe all the physical nature of such a system. So since we are all interested in the position and velocity, so we can define two independents as the order is 2, x1 should be the displacement and x2 is the x on velocity. By dx1 if we have f is equal to x2 on from this derivation, very simple, we can get a state space model defined in this way. So now we have got x dot equal ax plus bu. It is nothing but the metrics have been derived from this representation. Now D, it is 0, 1 over m. Definitely this system, and here it is called for the matrix notation in general and not necessary to be invertible. So if m is not invertible, algebra is coming in to study the effect of the m on such a dynamical system. We need to study here of the index of the matrix to divide the such a system into differential algebra. It is whether the system is differential or algebraic based on such a type of system in general called this vector system. But here we are assuming that m is non-zero, or the matrix m here it is definitely is invertible in robotic system, and here we assume that it is should be positive definite inverse matrix. As you one can see here, it is linear dynamical system. It is by the input, and it is how can we design such an input to make such a system will behave. Another model for this is called transfer function. If the system is linear, we take this is linear, Laplace transform for both sides. Definitely transformable, not necessarily some prior bound to such a status with the initial condition. Also, there is a good relationship between the output and the input, which called transfer function. Definitely for many types of the mathematical models are here. Because looking for another example of the dynamical system comes from electrical network system. To see, also we need to know the Kirchhoff's law in the current and Kirchhoff's law. If we give the input here as the voltage drops around this area by U1, and we have a resistance, the output which is going to the source, our source, and we have two resistors and two capacitors for such a dynamic system. So how can we derive a mathematical model? That mathematical model will give us a relationship between this input U1 and output U2. Or in another way, how can we get output as a solution of the motion of a dynamical system for a given input? Then later we have to ask for what kind of input should be given so that the output behave in a suitable manner. Then after that, an optimal control, how the optimal control is designed so that the output will have a good criteria to be satisfied based on the decision maker. Definitely, to derive such a model, we have to be assumed first of all, we know all of us, these laws, first of the short's voltage law, the sum of all voltage law around a closed loop are zero. We have here first closed loop, the second closed loop, and the third closed loop. So there is a voltage here, just this voltage here is given by IR. We have resistance, and the current is coming from here, so from the current and resistance we can get a voltage here. Also there is a voltage coming from this capacitance. This voltage based on the nature of this law equal 1 over c integration I dt. So these should be zero in a closed loop. Also we have the 0 and 3. So from this relationship, also from the Kirchhoff's current law, the sum of current I1 should equals to the I2 plus I3. From all of this information, mathematical model may be derived easily. Thus, it needs to be checked first. Now, I2 should be I1 minus I2 as the second law of the Kirchhoff, and the voltage we have the drop, the enclosed circuit, this is the 0, and from all of this information, as one can see, I will not go all of these details, but you can see first of all we have to eliminate, and you can little manipulation from this, U1 is written by this, you can get U2, U3, I1 over C1, I3, it is here, you can put all of these together, I will show you just in radically to see how the effect of such a region and just little manipulation one can get a mathematical model that can be used to this related to the output. Okay, now it becomes clear this relationship. Okay. Now, as one can see, what we have got by this simple derivation with respect to all of these details. Now, the input is here, and the output U2 is coming as an output as a solution of such a differential equation. You have a second order ordinary differential equation. The output represents its own unknown coefficient should be determined according to this equation. Definitely, we have to look for the relationship between the output for a given input. So definitely the input will affect the solution of the output. So input may be sinusoidal, maybe cosine, maybe any form, maybe feedback input, maybe open loop input, and this time of differential equation. Now trying to modify such a differential equation to get a steady state representation, which I was looking for this steady space to get a two-coordinate system as a system of the first order ordinate differential equation. So x1 should be u2 and x2 du by delta t. From all of this information, we can obtain now a steady space representation as this form x goes equal ax plus du, where a is a matrix given by this form du etc. Now, as you know, this system is a linear, finite dimensional because we are looking for positive domain. The solution is easily implemented using a joint system involving EAC function. But in infinite dimensional problem, this is not an easier thing. We have to look for the technology continuous summing rule of bounded linear attributed to suitable dynamics. To find our best to define domain and applying some result is used to the Fourier pseudo-generated theorem to get the solvability of such a system in general. We are looking for the infinite dimensional system. So once a mathematical model is derived, as we have discussed earlier, from the mechanical system, from the chemical using conservation of the mass in energy, one can using empirical or semi-empirical. So first of all, the plant to be, or process to be controlled has been derived. Now I just have to show you just a simple example of derivation of mathematical model. Definitely a huge number of the modeling of such a dynamical systems are taken in there. So once in general, let us consider with such a type of plant x dot equal FTXU, where x here is a state of the output sometimes, and u is the input or control. These parameters should be designed according to some specific requirement, mathematical. So optimal control, how it is controlled, or plant or process to be controlled should be designed first of all. Now, such a system, for example, linear, we have discussed all how can we derive such a system from a mechanical system and one from the electrical network process. Second, what type of initial and target state of the physical system? As you know, optimal control problem is a problem concerning many applications. For example, anti-craft missiles. As you know, anti-craft missiles, the dynamic of the craft is moving, and we have to make a radar follow this movement, and the missile has to follow such a moving target. So definitely the target here, initial condition and target has to satisfy some continuously moving compact target state. Even now, the missile or the missile now has its own radar, has to follow, just trying to make a fire and forget its own dynamical system. So it's called dynamic follow dynamic system. Initial condition also should be chosen appropriately based on the physical method. And the third point is the class of admissible control. So is it possible to find such a control that we are looking for to steering all the initial conditions to the target. So definitely this class of control should be the measurable function derived on various times. And the only aim we need to steer x0 to the target. Without this aim, we cannot make. So this delta class of admissible control should not be empty. Otherwise, we have no control of the concept. Definitely, the simplicity of designing offset control, whether the control is an open loop or feedback based on the state is the subject of the many authors. And finally, the cross-functional of the performance. So what type of a cross-functional should be defined such that the objective of the output satisfies something based on the physical nature of the problem. Definitely X and L are suitable continuous functions have some properties that will be designed later based on the nature of the physical. Now, optimal control problems can include of all of these. The plan first of all should be derived, the initial and tactical physical constraint, the movable and moving target point, the class of admissible control, as well as the cost of the performance engine should be defined. As you know from this plan, we have many information here for simplicity. Now let us some property of such a dynamical system. Nature of the system differentiation may be linear versus non-linear. And even this for linearity or non-linearity, for finite dimension it is easy to be implemented, but for infinite dimensional system need to be hard work. We have to go through the deep functional analysis, and we have looking for such stochastic continuous simulate or whatever or matrix simulate to solve for linearity, even for number of the input for the system. Here input may be single input or let's say multi-input, and when the input is interested in the system, negative will be out. Closed loop control system configuration. Definitely if you are looking for the washing machine is open, but if you are looking for your refrigerator in your home, the control effective on the freeze should be closed loop so that you can control the freeze temperature that board. For the missile problem, for the robotic system should be closed loop so that can be make elimination limit for disturbance that may happen to another dynamical system. So closed loop it is most important in such an application. Nature of the parameter, we have lambda parameter for distributed parameter system, we have looking for partial differential equation integral or even delay, we have to looking for distributed parameter system, but in general here we are discussing the simplest case problem, just we leave the other for question, maybe you can say for distributed mode of operation continuous or path, variability of the system time engineering. As you know, when launching a missile to the space, so his weightage will be reducing based on the fuel consumed. But due to the gravity sometimes will be increased, so the parameter at the time will be here is very and there is a large number of systems has internet time. Nature of similar simplicity, discrete dynamical system. I'm not talking about discrete. Dr. Ahmadi and Dr. Nadia has a total clarification on discrete dynamical system. Definitely the clarification for the unusual classical system is for safety. Very complicated nature of disturbance. Definitely here this is very important to affect on sophistication. If the system here disturbances come from probability nature, so Brownian motion or white noise will affect such a system. Definitely the system will not resume as this form, it will depend on the integration, or integration of the cover. So we have to look for the studying the statistical certificates. We're not looking for the solution, but looking for the nature of the statistical and how the probability will affect such a type of system, deterministic. So we need to define a stochastic process, not first order system. Reference input. So definitely the system has to its own reference input to be found. So many of these functions may be based on the nature of such output. Now let us talk about the mathematical property of this dynamical system. Definitely, since we are interested in AU, is a measurable function. If it is measurable, so all of this application P will be a natural function of T. Now, since we have to do this definition first of all, two functions are defined on a set difference and value all on every set are said to be equal almost everywhere. As we know, almost everywhere, first of all, is a very important in applied mathematics. So these functions are equals